In this video, we're going to take a look at exponent rules, and then we'll use those exponent rules to do some simplification and some problem solving. So the first idea is, what is the operation of an exponent? Well, when we have the operation of an exponent, we're going to take a number, which we call a base, and raise it to a power. Now, if we have natural number exponents, then that power is raising it to the p power is like taking our base and multiplying by itself p times. So if we have b to the first power, we just have b itself. If I have b to the second power, I have b times b. B to the third power is b multiplied times itself 3 times. So if we have a natural number, then b to the p power, or b to the exponent of p, means I have p factors of b multiplied times each other. So it's the same thing as repeated multiplication when I have a natural number as the power. Let's go ahead and calculate a few things. Let's do these calculations. So if we take 5 to the third, there's two ways we can calculate that. 5 raised to the third power, or 5 raised to the exponent of 3, is 5 times 5 times 5, which we can do by hand as 5 times 5 times 5. We can also type into our calculator 5 raised to the third power, and either way, you get 125. Doesn't matter which symbol we use, whether we use the cross multiplication symbol or the dot multiplication symbol, both of those mean the same thing. We can use parentheses as well. So there you go. 5 times 5 times 5 is 125. When I take negative 2.3 raised to the fourth power, I have to be really careful about multiplying negatives, because I'm going to get a negative 2.3 times another negative 2.3 times another negative 2.3 times another negative 2.3. Since I'm dealing with negative numbers, I'll use parentheses there. You can also, if you'd like, type it into your calculator and just take negative 2.3 raised to the fourth power. As a decimal, I get 27.9841. Now, if we're multiplying 3 copies of negative 3.5, or excuse me, negative 3/5, not negative 3.5, I'd take negative 3/5 times another negative 3/5 times another negative 3/5. Negative times negative times negative would give me a negative. And then the fraction I end up with is going to have 3 times 3 times 3 in the numerator, which is 27, and 5 times 5 times 5 in the denominator, which is 125. So you get that, or the decimal version of that. Now, if I take pi squared, well, those are things that I can type into my calculator. Pi obviously is an irrational number. So if I want the exact answer, I just have to keep it as pi squared. But if I'm willing to do an approximate answer, then I can just type in pi times pi, or pi quantity squared, on my calculator. That comes out to about 9.8696. And it keeps going on and on and on. There I'm rounding to 4 decimal places, but you could round to 2 or 3 or 4 or 5 decimal places, depending on what the question asks. But there you go. Hopefully you know how to type in exponents into your calculator and how to do repeated multiplication with your calculator. So that is the baseline of how natural number exponents work. We're going to take the baseline of how natural number exponents work, and we're going to extend that in 2 different ways. We'll look at how exponents must behave based on how natural number exponents will work. And then we'll extend those rules to other numerical values on exponents as well. The first rule we're going to look at is the product rule of exponents. Given any base and natural numbers m and n, if I take b to the m power and multiply it times b raised to the n power, that's the same thing as b to the power of m plus n. So the power is m plus n. Now, the reason that works is what we just saw. We have m factors of b multiplied times n factors of b. Well, m and n give you a total of m plus n factors of b. So that is b raised to the m plus n power. So we get m plus n factors of b. Once we know that, we can very quickly rewrite and simplify things if we have the same base. Now, this rule only works if we have the same base. If I had 2 different bases, I could not do this rule. So let's go ahead and simplify using this product rule. We'll assume that the bases are non-zero, otherwise it's uninteresting. And we'll assume that all the operations can be done. If you want to try this on your own, go ahead and push pause on the video. I will show you how it's done in a couple of seconds. All right, so for the product rule, if we have x to the 5th times x to the 9th, all we have to do, instead of writing out 5 factors of x times another 9 factors of x, I can simply say 5 plus 9 is 14, so I know that's a total of 14 factors of x. Now, if we have things where we have a term which has all multiplication times another term which has all multiplication, then what we can do is we can multiply these 2 things and use the product rule here as well. Now, here's why the product rule works. Because we have all multiplication in the first term and then times all multiplication in the second term, we can use the commutative property of multiplication. And we can say that I can move around the 2 and the 5, so they multiply times each other. And then the x to the 3rd and the x multiply times each other. And then the y to the 6th and the y squared can multiply times each other. Usually I don't write down that step. I just do that step in my head and say that means when I multiply using the product rule, 2 times 5, that's just numerical multiplication, that's a 10. X to the third times x, if you don't see an exponent, it's an implied 1. So that's x to the fourth. And then y to the sixth times y squared is y to the eighth. So 10x to the fourth y to the eighth is the final simplified answer there. Like I said, most times we don't do that middle step. We just think of it like that middle step. That happens in our head. Just like in this next one, we have -3 times 7. I would just write down -21. X to the 6th times x to the 8th. That's going to give us an x to the 14th. And then there's no y here, but there's a y to the third there, so we just end up with a y to the third. So -21 x to the 14th y to the third is the final answer. Now remember, that works because of the fact that we're multiplying everything in the inside and multiplying everything on the inside here. I'm taking a single monomial and multiplying it times another single monomial. That just means one term. All right, let's take another rule. Another rule that we can figure out quite easily using natural numbers is called the quotient rule. Given any non-zero base and natural numbers m greater than n, so m and n are both natural numbers and m is the bigger one, then taking b raised to the m power and dividing it by b raised to the n power is b to the m minus n power. Now, the reason for that is that there's going to be m copies of b on the top and only n copies of b on the bottom. You can put the rest of the b's over 1, but every b over b will get canceled and just become the numerical value of 1. So we get 1 times 1, and so on and so forth times 1, and then we get a bunch of b's. So we get n times where they cancel each other out, and the leftovers will be m minus n. And so that's just b to the m minus n power. So let's simplify here. Again, we'll assume the bases are non-zero and all operations can be done. By the way, the reason we're assuming that the base is non-zero is because we don't want to divide by 0. Dividing by 0 is undefined. So let's do this. Y to the 6th divided by y squared. And then we'll do 12x to the 8th, y to the 4th divided by 8x squared y. Go ahead and push pause on the video and do this one on your own if you'd like. In a couple of seconds, I'll show you how each of these two are done. All right, so on this first one, we have y to the 6th divided by y squared. That's 6 copies of y divided by 2 copies of y. And essentially, these are canceling out. When you cancel out, you get ones, and 1 times anything is itself. So we're left with 4 copies of y, and that's it. That's the whole thing. So we end up with y to the 4th. Usually we don't write this middle step. Usually we just say 6 minus 2 is 4, so that is y to the 4th. And that's the quotient rule. It's saying we don't actually need this middle step. We can just say y to the 6th divided by y squared gives me a y to the 4th. In a similar way, if we have a monomial divided by a monomial, I can take 12 divided by 8. That, by the way, simplifies to 3, 4, excuse me. No, 12 divided by 8, 3 halves. Divide each of those by 4. So that simplifies to 3 halves. X to the 8th divided by x squared would give me an x to the 6th power. Y to the 4th divided by y to the 1st gives me y to the 3rd power. Excuse me. So there you go. Quotient rule allows me to do that type of simplification. Now, in all of the rules that we've been looking at the really nice case where our exponents are natural numbers. So now we're going to do our first extension of these exponents. And the first extension is what happens if the exponent is a 0? So this is the 0 exponent rule. It says if I have any non-zero base, then if I raise b to the 0 power, it has to be 1. Now the reason for this is twofold. First off, we want to match our quotient rule. Notice that if m and n are both 1, then m minus n would be a 0. So this is like taking b to the 1st divided by b to the 1st. B over b is just 1, and therefore b to the 0 power is also needing to be 1. So b over b, using the quotient rule, would be b to the 0 power. But also using common sense, b over b is equal to 1. So if we want it to match up, if we want all of these rules to be consistent and match with my previous rules, I need b to the 0 power to be 1. Another way people talk about that is they'll say b to the 0 power means no factors of b. And the identity in multiplication is the number 1. So if you don't have any multiplication going on, b to the 0 power, that's no factors of b, gives you the identity in multiplication, which is 1. Now, to extend this even further, we can go and look at negative exponents as well. If I take b to the negative n power times b to the positive n power, by my product rule, if I want my product rule to work for exponents that are not natural numbers as well, then combining these would give me b to the negative n plus positive n, which is b to the 0, which we just saw was 1. But we also know that b to the nth power divided by b to the nth power would also give me 1. So b to the negative n power is like 1 over b to the positive n power. And this rule allows me to deal with negative exponents. Negative exponents are reciprocals of things with positive exponents. So b to the negative n power is 1 over b to the n. By the way, this works if n is negative as well. 1 over b to the negative power is equal to b times to the positive power. And that gives me another negative exponent rule. 1 over b to the negative n power is equal to b to the positive n power. 1 over b to the positive n is equal to b to the negative n. And then lastly, if we have a fraction where a and b are both non-zero, then a over b to the negative n power is like the fraction b over a raised to the positive n power. That's because b over a and a over b are reciprocals of each other. And again, that all comes from the idea that the multiplicative inverse of b to the negative n is really the same thing as dividing by b to the n. So b to the negative n is the multiplicative inverse of b raised to the positive n power. That's what these two say. And multiplicative inverse is the reciprocal. So fraction to the negative power is like the reciprocal fraction raised to the positive power. Let's go ahead and simplify these. Let's assume all the bases we deal with are non-zero, so we never have to divide by 0, and that all the operations can be done. We will write answers with positive exponents if we have a choice. So if you want, go ahead and push pause on this video. Try these two problems. In a couple of seconds, I'll show you how these are done. So the first thing we have to establish is that 4 is just a numerical value. So 4 is not going to be changed from denominator to numerator or vice versa. X to the 5th already has a positive exponent on it. So I'm going to keep that as x to the 5th. Lastly, we have y raised to the negative 2nd power. Well, that is y raised to a negative power in the denominator. I can rewrite that. Instead of dividing by y to the negative 2nd power, I can rewrite that as multiplying by y raised to the positive 2nd power. Now there's no other simplifications I can do. 4 times x to the 5th times y squared would be my final answer. All of the exponents that you see there are positive, and therefore we're done. Now we can do a very similar thing. Excuse me. Sorry, something weird happened. We can do a very similar thing with this next problem. So we have -7. That is just a numerical value. Don't get thrown off there. A negative numerical value is not the same thing as a negative exponent. So -7 would stay in the numerator. On the other hand, a to the -1 power, we can flip that to the denominator. Since it's currently in the numerator, we flip that into the denominator and call it a raised to the +1 power, or just a. And then b raised to the -12th power is going to be b raised to the 12th power when I put it into the numerator, since it used to be in the denominator. So anything with a negative exponent in the numerator can be swapped to the denominator and then forced to have a positive exponent, or vice versa. Any negative exponent in the denominator can be swapped to the numerator and have a positive exponent. So there you go. That would be the final answer for both of these problems, because now all of the exponents we're using are positive exponents. Again, that's different than negative versus positive coefficients. That doesn't throw anything off. This is only a rule for exponents. Now, I wanted to do the zero exponent rule and the negative exponent rule before I do this next rule, which is the power rule, because the zero exponent rule and the negative exponent rule come straight from the quotient rule applied to other scenarios. But here is our next rule. We have the power rule of exponents. Given any base and natural numbers m and n, we can take a base raised to the m power and then raise that whole thing to the nth power, and we get b raised to the m times n power. Now, the reason for that is we have n copies of b to the m. And if you have n copies of something, if I do the product rule over and over and over, I get b to the m times n. So if this were 3 m's, that would be 3 times m in the exponent. If this were 4 copies, I'd get 4 copies of b to the m, which would be 4m in the exponent, and so on and so forth. So based on how exponents have to work, the power rule for exponents has to work this way. Now, there's other power rules as well. If we're multiplying two numbers and then raising the whole thing to the power n, we can apply the power n to both numbers. If we do that with division, since division is the inverse operation of multiplication, we can do that with division as well. So a over b, all raised to the nth power, is like a to the nth power divided by b to the nth power. Let's calculate and simplify these two examples. We'll assume all the bases are non-zero. We'll assume all of the operations can be done. And then we'll write our answers with positive exponents. Go ahead and push pause on this video if you'd like and try these on your own. In a couple of seconds, I'll show you how these are done. I'm going to go ahead and do these, and I'm going to write the intermediate steps in on all of these. Sometimes people will not write the intermediate steps, but I'm going to write the intermediate steps. We're going to take 5, the number 5, raise it to the 4th power. We'll take the number a to the 3rd and raise it to the 4th power. And then we'll take the number b and raise it to the 4th power. Now, when I take 5 and raise it to the 4th power, that's just a numerical calculation. So that's going to be 625 when I type that into my calculator. These next two, we're using the product rule. A to the 3rd raised to the 4th power is going to be a raised to the 12th power. And b to the 1st raised to the 4th power, well, 4 times 1 is 4. That becomes b to the 4th power. And that's it. That's the final answer. All of the exponents are positive. I don't need to rewrite anything beyond that. In the second problem, we would have -2 raised to the third power, then a to the -6 raised to the third power, and then divided by b raised to the fourth power raised to the third power. B to the fourth raised to the third power. So this would be applying that power rule. Every number gets raised to the third power. That's because everything is either multiplied or divided. If we have a plus sign in there somewhere, we'd have to deal with this in a much different way. Now, -2 raised to the third power is -8. Using the product rule, a to the -6th raised to the third power would be a raised to the -18th power. 3 times -6 is -18. And then b to the fourth raised to the third power is going to be b to the 12th. And there we go. Now, we're not quite done because one of our variables is being raised to a negative power. So the question asks us to make sure that all exponents were positive. That's exponents, not numbers. So it's perfectly fine that -8 is in our final answer. -8 is a coefficient, not an exponent. But a to the -18th in the numerator changes to a to the +18th in the denominator. B to the 12th in the denominator, since it's already being raised to a positive power, is going to stay in the denominator. So my final answer would be -8 divided by the quantity a to the 18th times b to the 12th. So those are our main rules of exponents. We had a product rule, a quotient rule, zero exponents rule, negative exponents rule, and then lastly, we had this power rule. Now, all of our exponents so far have been integers. They've either been natural numbers or zero or negative natural numbers. Now we're going to deal a little bit with rational exponents. If we have a positive base and n being a natural number, then b to the 1 over nth power has to be the number you get, or excuse me, the number that when you multiply it times itself n times, you get b. So if I do b to the 1 over n times b to the 1 over n times b to the 1 over n times, if I add up 1 over n times, I get a 1. If I want the product rule to work in this case, this has to be true. And that means I multiply it times itself n times, I get b to the first, or just b. Now, the number you multiply by itself n times to get b is also called the nth root of b. This is why we wanted a b to be positive, so that we don't have to worry about negatives underneath a square root. So the nth root of b is b to the 1 over nth power. and b to the 1 over nth power is the nth root of b. Now we can say, well, what's going to happen if we did 2 over n, or 3 over n, or 4 over n, or any m over n? Well, if b is positive, if I have a positive base, then b to this fractional power, this fraction could be proper or improper, doesn't matter, is the nth root of b to the m, or the nth root of b raised to the mth power. And b to the negative 1 over n is going to have to be 1 over the nth root of b. It has to work this way if I want to maintain the power rule that we saw here. If we want to maintain this power rule, then exponents have to work this way. Let me explain what I mean by that. So b raised to this fractional power, you can think of this as b raised to the 1 over nth power raised to the power m. And remember, b to the 1 over nth is the nth root of b. So that's exactly what we have here, just rewritten. Those two are identical from what we know of b to the 1 over n power. But we could have also written this as b raised to the mth power, all raised to the fraction 1 over n, which is exactly what this one is. M times 1 over n is m over n. 1 over n times m is m over n as well. So if I want the power rule to work with other exponents, then I need my rational exponents to all work this way. And the same thing with negative of rational exponents. I can simply say this is like b raised to the 1 over n power raised to the negative 1 power. That's the reciprocal of 1 over b to the 1 over nth power, which is 1 over the nth root of b. So things like square roots and cube roots and fifth roots are all just like raising an exponent to a fractional power. 1 over 2, 1 over 3, 1 over 5. And we can extend that to 2 over 3 power. And we can extend that to the 7 over 5 power. And so on and so forth using these tricks or these rules. So let's calculate or simplify these expressions, and we'll do so without a calculator to begin with. So 125 raised to the 1/3 power, 81 raised to the 3/4 power, and 8 raised to the 4/3 power. If you want to try this on your own, go ahead and push pause on the video. Otherwise, I'll show you how it's done in a couple of seconds. All right, so 125 raised to the 1/3 power is like taking a third root of 125. So we're looking for the number that when you multiply it times itself 3 times, you get 125. Earlier in this video, we saw that 5 times itself 3 times is 125. So that 125 raised to the 1/3 power should be equal to 5, and in fact, it is. Here we have 81 raised to the 3/4 power. There's a couple of different ways you can do this. Probably the easiest way is to take the 4th root of 81 and then take that whole thing and raise it to the 3rd power. That's one of the options for doing these things. And the 4th root of 81, that's the number I have to multiply times itself 4 times to get 81. That's 3. So that's 3 raised to the 3rd power, which is 27. I'll write that on a new line. So 81 to the 3/4 power is 27. Similarly, if we want to take 8 and raise it to the 4/3 power, what I would do is I would say, let's take 8 and the 3rd root of that. Remember, the denominator is determining the size of the root there. And then raise that thing to the 4th power. The 3rd root of 8 is equal to 2. 2 times 2 times 2 gives you 8. And then we're going to take 2 and raise it to the 4th power. If you do that, 2 to the 4th power is 16. And so that just becomes 16. Now, this is not the only way you could have done this problem. And similarly, this is not the only way you could do this problem. But if you do it the other way, then you end up getting some bigger values that you have to work through. So for instance, if I took 8 and raised it to the 4/3 power, and I did it the other way, meaning I take the 3rd root of 8 to the 4th, what I'd have to do is calculate 8 to the 4th first, which is 4,096. And I'd take the 3rd root of 4,096 and I'd say what times what times what gives me 4,096. That's a little bit harder to come up with if you don't have a calculator. It's still 16, but it's harder to see that 4,096 comes from 16 times 16 times 16. So I tend to take the roots first if I can, and then raise them to, like in this case, the 4th power. That way I'm dealing with smaller numbers. But technically you can do it either way. I should specify you can do it either way so long as this base is positive. So long as we have a positive base, we're good to go with that. Now, you can also calculate and simplify with a calculator. You can simply type in to your calculator 5 and raise it to the 1/2 power, or 81 and raise it to the 1/5 power, or 7 and raise it to the 5/2 power, or any of the ones we did before. And as long as we type it in correctly into our calculator, we should get the correct answer. So in our earlier problems, in our previous example, if I would have just typed in 125 and then raised it to the 1/3 power, I would have got 5 without even having to do a middle step. Or 81 raised to the 3/4 power, I could have gotten 27 without doing a middle step. Or 8 raised to the 4/3 power, I could have gotten 16. Here, I have a couple of different options. Usually, what I do is I just do 5 raised to the 1/2 power and making sure that the 1/2 is always in the exponent. The 1/2 is actually in the exponent. You're either going to get, in an exact answer, would be square root of 5, but square root of 5 is actually an irrational number. And therefore, if you're writing this as a decimal, you can only get an approximate value. 2.2361, if I'm going out to 4 decimal places, is the approximate value for the square root of 5. That means if I took that 2.2361 and multiplied it times itself, then I would get about 5. If I take this exact value, the one that's in my calculator right now, and I multiply it by itself, I'd get exactly 5. Same thing with 81 raised to the 1/5. You can say, well, that's going to be the 5th root of 81. By the way, some calculators, you can easily type in the 5th root of 81. I tend just to type in 81 raised to the 1/5 power. And 81 raised to the 1/5 power would be about 2.4082. And if you took that 2.4082 and raised it to the 5th power, you'd get about 81. I should write the approximate symbol there because I did round that to 4 decimal places. A lot of times in my class, I'll round to 2 decimal places, but I want to go out just a bit further here so you make sure you get the same thing I did on my calculator. And then lastly, 7 raised to the 5/2 power. If we were doing that as a root, it'd be the square root of 7 raised to the 5th power, or the square root of 7 all raised to the 5th power. And that also is an irrational number. And the decimal approximation of that is 129.6418. Again, I'm going out 4 decimal places on this video, but other times someone may ask you to round it to 2 or 3 or maybe the nearest whole number, who knows. But there you go. That's the idea of these rational exponents. So anytime I can write my exponent as a improper fraction, then I can use roots to calculate. A lot of times I might get irrational numbers as the answer because a lot of numbers like 7 don't have nice square roots, or 81 does not have a nice 5th root, or 5 doesn't have a nice square root either. Now this brings us to our last type of exponent. And that last type of exponent is an irrational exponent. So an exponent like pi or the square root of 5, or the square root of 2? Well, if I want to calculate b raised to an irrational exponent answer, to an irrational exponent number, then I always have to force this rule that if there are two numbers, one which is smaller than my p and one which is bigger than my p, then this has to be the case. B raised to the q1 has to be smaller than b raised to the p, has to be smaller than b raised to the q2 power. So we get this feature for all values of b that, well, let me add on one little caveat there. And here's that caveat. So when b is above 1, then higher exponents make the number grow. And when b is below 1, that is above 0 but below 1, then the higher exponents are actually making the number smaller. So the point is, when we have two values on either side of p, then b raised to the p power has to be in the middle of those two values. So for instance, if I raise something like 2 to the pi power, since 3.14 is smaller than pi and 3.15 is bigger than pi, 2 raised to the pi power has to be somewhere between 2 raised to the 3.14 power and 2 raised to the 3.15 power. Let me write that down. So 2 to the pi has to be between 2 to the 3.15. 3.15 is a rational number. 3.15 can be converted into an improper fraction. That fraction would be 63 over 20. And 3.14 can also be converted into an improper fraction. That improper fraction would be 157 over 50. Let me rewrite that in the more common sense way of converting it. It'd be like 314 over 100. And this would be 3.15 would be like 315 over 100. Both of those can be calculated because both of those are rational exponents. And so the irrational exponent has to come between there. The 2 with the irrational exponent has to come between there. Now, we can keep getting closer and closer and closer to the right answer using rational exponents because we can always go out further and further and further. So for instance, pi is 3.14159. So if I go out 3 decimals, I know that pi is somewhere between 3.141 and 3.142. And then I could narrow this down. I could keep going out further and further decimals and show what 2 to the pi power has to get close to. Now, the nice thing is that using our calculator, we can actually just type this in. We can type in 2 to the pi power. And we can get a very good approximation. In this case, it's about 8.8250. That's when I round to 4 decimal places. Obviously, if I'd round to 1 decimal place, it'd be different. But 8.8250 when I round to 4 decimal places. By the way, that would round to 8.82 if I rounded to 2 decimal places. So in this way, we can take any exponents that we want, not just rational exponents, but now I can deal with even irrational exponents. And that allows me to extend these exponent rules to any real numbers. As long as my base is positive, then I can extend these exponent rules to any real numbers. And we get b to the mth power times b to the nth power is b to the m plus n. B to the m divided by b to the n is b to the m minus n. 1 over b to the n is b to the negative n. And then b to the m raised to the nth power is b to the m times n power. So all of my exponent rules work as long as my base is positive and my m and n are real numbers. And so we don't necessarily think at this point when we use real numbers, we don't think of an exponent as being repeated multiplication anymore. We've extended that, and now we have an exponents, or our operation of exponents, to be this new calculation that meshes with repeated multiplication when we have natural numbers, but extends much beyond just the rational numbers, or just the natural numbers. So we get our product rule, our quotient rule, our negative exponent rule, and our power rule with all real numbers now. And furthermore, because we have these properties, we can use these properties by applying the exponent rules in reverse when solving equations with a variable in the base. So for instance, if I want to solve x to the fifth is equal to 7,776, or x raised to the 1/3 power is equal to 12, I can apply the exponent rules in reverse to solve those equations. Let me show you how I would do that. So since x to the fifth is 7,776, what I could do is I could take that x to the fifth and I could raise that left-hand side times the to the 1/5 power. If I do that on the left-hand side, I do that on the right-hand side as well. And since 7,776 is a positive number, I can perfectly apply that rule. I can type this into my calculator, 7,776, and then raise that to the 1/5 power. On the right-hand side, I get 6. Now on the left-hand side, using the power rule, 5 times 1/5 would just be 1. So that'd be x to the first, or just x on the left-hand side. And on the right-hand side, I get a 6. You could have also taken the fifth root, because we know 1 over 5 as an exponent is the same thing as the fifth root. And the fifth root of 7,776 would have been 6. In a similar way, if I have a 1/3 power, I can just take both sides and raise it to the third power. Again, I'm assuming all these bases are positive when I solve this. If I didn't explicitly state that before, we're going to assume our variable is positive. And 12 raised to the third power is 1,728. So that's how you can use these exponent rules along with, well, along with what we know about exponents to solve equations where a variable is in the base. And your exponents don't need to be positive. They don't need to be rational numbers. They can be any numbers that you want. Go ahead and try this one on your own, utilizing your calculator. These are going to end up as irrational numbers, probably. So you'll have to use your calculator to do some of the calculations. And I'll ask you for an approximate value for x when I do this. Go ahead and try again these two on your own. In a couple of seconds, I'll show you how these are done. All right, so let's go ahead and do this. Now, there's actually a couple of different ways you can do this problem here. You could use the negative exponent to indicate reciprocals first if you wanted to, or you could do it this way. I'm going to take both sides and I'm going to raise both sides to the power 1 over negative 4.1. So I'm going to raise to a really kind of awkward power, 1 over negative 4.1. But when I do that, 1 over negative 4.1 times negative 4.1 just gives me a 1. That's just x on the left. On the right, I'd have to utilize my calculator. When I utilize my calculator, I get approximately 0.8162, rounding to 4 decimal places. So that's one way to do it. Another way to do it is to say, well, since we had x raised to a negative power being 2.3, x being raised to the positive 4.1 power would have to be the reciprocal of 2.3. So the reciprocal would be 1 divided by 2.3. And then I could raise that thing both on the left and right-hand side of that equation to the 1 over a positive 4.1 power. And you get the exact same answer of 0.8162. But in this one, we just use reciprocals first and then raised by 1 over a positive power. Here, we just use the negative power. In a similar way, we can raise each side of this equation to the 1 over pi power. So I'd take 7 and raise it to the 1 divided by pi power. That's not something that I can do by hand. In fact, that's an irrational exponent. But I can have my calculator give me out an approximate value for that. And when I have my calculator give me out an approximate value for that, it's about 1.8578. Again, I am rounding to 4 decimal places. You may be asked to round that to 2 decimal places or another decimal place value in your homework. But there you go. That allows us to solve these basic exponent equations where the base is a variable. You can also solve equations with square roots and fifth roots, at least the basic equations with square roots and fifth roots, using what we know about rational exponents. So here we have square root of x is equal to 15, and we have the fifth root of x squared equaling 9. Again, we can utilize what we know about rational exponents, what we know about our power rules, our exponent power rule, and solve for x in both of these. In the first one, I just realized that I try to realize that this is just x raised to the 1/2 power equaling 15. And so I can simply square both sides. To get the answer that I'm looking for. If I take 15 and square it, I get 225. So that means x is 225. Now for the last one, interesting. Oh, and by the way, if you took the square root of 225, you get 15. You can check that out by taking 225 to the 1/2 power and getting 15 as well. So the last one is kind of maybe the most interesting one. On the left-hand side, this is x raised to the 2/5 power. So if I'm trying to undo that 2/5 power, I'm going to raise both sides to the 5/2 power. 2/5 times 5/2 gives me 1. And I'd do the same thing on the right-hand side as well. I'd take 9 and raise it to the 5/2 power. Now, if I take 9 and raise it to the 5/2 power, I end up with 243. And that is a number that when I take and square it and then take the fifth root, I would get 9. So that is a number that works in this equation. Now, interestingly enough, also in this equation, x equals negative 243 would have worked in the original equation too. My exponent rules, when I wrote them down, we assumed always that our base was positive. But in this case, because we square before we take a fifth root, when I square the negative 243, I'll get a positive number, specifically 59,049. So if I square the negative, then it'll change into a positive number, and I can take the fifth root of a positive number as well. So x equals negative 243 also works. Sometimes In a question, they may only ask for the positive values of x that will work, and then you don't have to worry about like the negative 243. Other times, you may have to check whether the positive and the negative version of that number will work. In our previous problem, the square root, the negative of 225 would not work. If I tried to take the square root of a negative number, I would end up with an imaginary number. So something that does not give you 15. But in the second problem, the positive version and the negative version both worked. And again, depending on the problem and the homework, it may only ask for the positive version. It may ask for both the negative and positive versions. Hopefully that all makes sense. The big finding was that exponent rules work in lots and lots of situations. Anytime b is a positive number and m and n are real numbers, then these numbers work, or these rules work. You could also have b be a negative number as long as m and n are integers, and these rules will work as well. So if b is a negative number and m and n are integers, this rule works. These rules work as well. And it kind of just depends on your base and your exponents when the rules work, when you can do those operations, and when you cannot. So there we go. This is the end of the video on these exponent rules.